Hello everyone. In this video I'm going to solve at least 3 or 4 Bayesian problems. So the first problem is as shown on the screen. So out of 4 basketball games, John won 3 games and Harry won 1 game. So if you ask who won, clearly John won. But if you add another factor, when it is raining, John won 1 game and Harry won 1 game. So the question is, if it is raining on the next match, what is the probability that Harry wins? So how do we solve about it? This one actually, in fact, it is very straightforward, but we'll try to represent in the form of a Bayesian theorem and solve it. So let's do that. So as usual, I'm going to just review what is a Bayes theorem and Markov chain rule. So it says if the probability of A given B can be expressed as probability of B given A into probability of A by probability of B, right? And also you have a chain rule, probability of A B is equal to probability of A given B times probability of B, which is equal to probability of B given A times probability of A. So this intersection of A and B can be expressed as in this form, and you can simply see that Bayes theorem, if you put it in the denominator, it's a derivation. You can derive Bayes theorem. So this rule is known as Markov chain rule. I think in fact I'll just extend it to more variables and try to show how it looks like. So A given B C D, probability of B given C D, probability of C given D times probability of D, right? In fact the order need not be the same. You can actually have something like this: probability of C given AD times probability of A given D times probability of D. So the order can be anything. So these three represents Markov chain probability rule, and using these you can easily derive Bayes theorem. So let's go back to the problem and look at it. So in this case, what you have here is out of 4 basketball games, John won 3 games and Harry won 1 game. So we want to but if it's raining, John won 1 game and Harry won 1 game. So the question is, if it's raining on the next match, what is the probability that Harry wins? So let's look at the let's solve the problem. So clearly, what is the probability that Harry wins? This out of 4 games, Harry won only once, so 1 by 4. What is the probability that it rains? So this one is there are 2 games, right? One John won, one Harry won. So 2 games when it was raining, so it's actually 1 by 2. And then now the probability that it's raining, given that Harry is 1, Harry 1. So there is only one scenario where Harry won, and that was during raining. So you can clearly say this probability is 1. So the question is, what is the probability of Harry winning given it's raining? So simply this is a probability of raining given Harry won times probability of Harry winning divided by probability of rain. This one is probability of raining. You can just plug in the values from here. Probability of Harry winning is 1 by 2. Actually it's 1 by 4 times probability of it rains is 1 by 2. So this is essentially 1 by 2. In fact, it can be easily seen from the problem itself, but I'm just trying to represent in the form of a Bayesian problem, and this is how you derive. You can see that if when it's raining, each has equal chance of winning, so you can easily say that if it's raining, Harry has same chance as John, so you just submit. You can say it's half. You don't have to solve this way. Okay. Having done this problem, let's look at the next problem here, which is so that the second problem is 50% of the people who receive first interview also receive second interview. Okay, and 90% of your friends that got a second interview felt they had good first interview, whereas 70% of your friends that did not get a second interview felt they got a good first interview. So the question is, if you feel that you had a good first interview, what is the probability that you receive a second interview? So let's represent these terms in terms of probabilities, so that we can easily answer this problem. So the first step is so let's write down. So here what is it? The probability of second interview, or let's say probability of S. This is half, right? It said 50%, so it's half. What's the probability of feeling good? I guess I'll just say FG, feeling good, given second interview. Given they went to second interview and felt good in the first interview is let's say probability of F, feeling good, they got a second interview, is equal to 95%. And then we are also probability of feeling good when they did not go to second interview, is our second interview, is equal to probability of feeling good when they did not get the second interview, is 75%. So the question here is about asking if so the question is about what is the probability that you go to the second interview and you given that you felt good in the first, given that you felt good, what is the probability that you get a second interview? That was the question, right? Given that, so this is what we need to compute. So you can say probability of GF given S times probability of S by probability of GF. So we can expand this one and write as probability of feeling good given S times probability of S by probability of GF given S times probability of S plus probability of feeling good given not S times probability of not S, right? So this one you can write it as probability of feeling good given S is given as 95.0, okay, 0.95 times probability of S is 0.5, and then you have 0.95 times 0.5 plus 0.75 times 0.5. So yeah, I think if you compute this one, you will get a value of 0.5582. Okay, it's 0.5582. This is the probability. So one question is like, the interviewer actually ask, is actually telling about your friends. 95% of your friends got a second interview and 75% of the they failed. So it doesn't necessarily means you should feel like your friends, but you can make an assumption that you are like your friends, and you can substitute those values in there. So that is something that you can actually specify during the interview if you have one, but essentially this is the way you can solve it. So okay, let's look at one more problem. Which is, this is not really a Bayesian problem, but we can actually look at how to solve this one. A couple has two children. The older one is a boy, and then what is the probability that they have two boys? That's the first question. So the condition is that the older one is a boy, and what is the probability that they have two boys? And in the second case, couple have two children, one of them is a boy. What is the probability that both are boys? So this is actually straightforward, doesn't really require Bayesian. If you want, you can use it, but let's solve without using Bayesian theorem. Okay, let's say so this is essentially like probability of all possible events, all events by what you need, in this the required events by probability of all events, the whole sample space, right? So what is a sample space? So you can have, in the first case, it's a older person is a boy. Let's say the first one is boy, and the second one can be a girl, or first one is a boy and the second one is also boy. So this is the sample space. The question is asking what is the probability that both of them are boys. So there is only one chance of both of them boys is equal to 1. So you can say 1 by 2, right? So this one will solve the first problem. Second problem is the older second problem is essentially older. It doesn't talk about older one, but it just says one of the boy is one of them is a boy. What is the probability that both of them are boys, right? So in this case, sample space, what is the sample space? You can have boy boy girl, or girl boy, right? So one of them is boy in each of these cases. So this is the whole of sample, but both of them boy is only one case. So you can say this one is 1 by 3. So it doesn't really require a Bayesian solution, but I think it's good enough. Let's look at one more problem before we wrap this video. This one actually requires a Bayesian solution, so let's read it. In a manufacturing factory, machines A, B and C produce 25%, 35% and 40% moles respectively. Out of the total, the machine A produces 5% defectives, machine B 4% and machine C 2% defective bolts. Now if you draw a bolt at random from the product line, if the bolt is found to be defective, what is the probability that it is manufactured by machine B? So that is the question. So it's actually very classic Bayesian problem. So let's try to solve it. Okay, let's see. Let me change to the pen mode. Okay. Okay, so what you have here is a probability of the event happening from machine A is 25%, right? 25.25. Probability that a product, a bolt is manufactured in machine B is 0.35, and probability that the bolt is manufactured by machine C is 0.40. And then you also see that probability of defect item coming from EA, right? If the event happened in EA and the probability of the item being, the bolt being defective is 0.05. Probability of defect given bolt is coming from EB is 0.04. Probability of a defect bolt coming from machine C is 0.02. So this is what is given, and we are asked what is the probability that a bolt is defective. So it is given defective. Now you want to compute EB. So this is very straightforward. You just apply D given EB by times EB by probability of an item being defective, right? So this one, the numerator you can actually substitute, but which is what EB, right? So it's coming from B, which is 0.04 times probability of EB is 0.35, right? But the denominator is let's expand the denominator. You can have a defect item coming from EA times probability of EA plus probability of defect item coming from machine B times probability of EB plus probability of a defect item coming from event C times probability of event C. So if you substitute these values, so let's substitute these values, and you will see it's a 0.4 times 0.35 by 0.4. Actually it's 0.5 times 0.25 plus 0.4 times 0.35 plus 0.4 times 0.2. This is this will come down to 0.0405. This is a very classic problem, and this is where Bayesian theorem excels at. So it's actually pretty high. Okay, that's all the Bayesian problems we are going to solve.